The other major topic we're going to talk about in this section is piecewise defined functions. A piecewise defined function is a function that is defined by different equations on different parts of its domain. Okay, so in a nutshell, what a piecewise defined function is, it's a function that comes in different pieces. Okay, so you may have a piece of one graph and then a piece of a different graph and then even maybe a piece of a third graph and so on. Okay, so your graph comes in different pieces. Okay, so I've got 4 different examples planned for us. Okay, so if you look down at example 1, here is what a piecewise defined function looks like. Okay, so let's kind of just examine this function. The function, you still have your function notation f of x is equal to, but then you have this open brace and you have more than one rule that comes along with the brace. Okay, so if you look in this, we have a first rule, 5 plus x. You're going to use that rule if your x values are less than 0. Okay, so I'm going to go ahead and say this is rule 1. Okay, and then there's a second rule here. Your rule is going to be x squared, and you follow that formula if your x values are bigger than or equal to 0. Okay, so I'm going to go ahead and call this one rule 2. Okay, so this particular function has 2 different rules, so that means when you graph it out, you'll have 2 different pieces. With a piecewise defined function, you can have as many rules or pieces as you want. Okay, we'll stick to either 2 rules or 3 rules, but theoretically you could have 100 different rules if you wanted, or 1,000 different rules if you wanted. Okay, so a piecewise defined function just means you're having multiple rules in your function, so that when you graph it, you end up with multiple pieces to your graph. Okay, so what we're going to be doing with these piecewise functions, I've got, like I said, 4 different examples, and each one is set up the same way. Okay, we're going to take each piecewise function that we get, and we're first going to talk about how you would graph it. Now, keep in mind, when we graph these guys out, okay, they are functions. Okay, so it's not going to be like, okay, I'm going to take all of rule 1 and graph it, and then I'm going to take the entire rule 2 and graph it. Like, see what happens if you did that here. 5 plus x, you can write that in y equals mx plus b form. It's a line. So if you graph the entire thing out, you'd end up with some line. And then if you went back and you did x squared and graphed the entire parabola out, what happens here? Well, you violate the vertical line test, okay? And then that's not a function, okay? So that's not what you're doing. You're not graphing the entire function out or the entire rule out for each rule. Okay, you're only graphing a piece of it out. Okay, whatever you graph absolutely has to pass the vertical line test. Okay, all right, so we will graph out the function. Okay, after we have the graph, we will evaluate the function. Okay, meaning, if you plug in a certain x value, what's the y value going to be? Then we will examine the domain and range of each function. And finally, in part D, we'll talk about continuity of the graph. Okay, so continuity, the idea of a continuous function may be new to you, but we will talk about that when we get there. Okay, all right, so we are going to start off graphing this particular function. Okay, I'm going to have a specific method I would like you to follow. The way I do this, we make a table of values for each rule. Okay, I do this to kind of minimize your chance of making a mistake. Okay, so try to follow that method. It's very helpful. Okay, all right, so let's get started on graphing this particular function out. Okay, again, we have 2 rules. Okay, notice I put rule 1 in red and I put rule 2 in blue. So when we graph this out, I will put we have 2 rules here. That means we're going to have 2 pieces on our graph, and I'm going to color code them. So everything that comes from rule 1, I'll put in red, and everything that comes from rule 2, I will put in blue. So you can kind of follow what comes from which rule. Okay. All right, so like I said, we're going to make a table of values for each rule. Before we do that, I need you to look at these if conditions, okay? These if conditions are very, very important, okay? The 5 plus x, like I said, we're not going to graph it in its entirety. It's only going to exist if the over the x value is less than 0, okay? And then the second rule, x squared, it is only going to exist for x values bigger than or equal to 0. So you have to pay attention to the if conditions, okay? The first thing I'm going to do before I even make the table of values here, I need to recognize where the rule changes. Okay, it's going to be different for every piecewise function. Here, the rule changes at x equals 0 based on these yellow conditions. Okay, let me put that in a different color so you don't confuse it. Okay, so the rules change at x equals 0. Okay, to the left of x equals 0, we're going to have one rule, and then to the right of x equals 0, we're going to have another rule. Okay, I cannot emphasize enough. For this particular function, the rule changes at x equals 0, but for a different function, it may change at x equals 1, or it may change at x equals -2. It is not always at x equals 0. All right, so first thing we're going to do is recognize where the rule changes. The rule changes at x equals 0. So what I'm going to do, okay, here's where x equals 0, right here, okay? I am going to put a dotted line here, okay? And I'm putting it in green. Hopefully you can see that, okay? This is not part of the graph. This is not part of the graph, okay? This is just a reminder to me, okay? You cannot cross this vertical line, okay? To the left of the vertical line, we're going to have one graph. To the right of the vertical line, we're going to have a totally different graph, okay? If you cross that line, essentially you're going to be violating the vertical line test, okay? So this, again, not part of the graph, just a reminder, this is where the rule changes. You can't cross the line, okay? All right, let's get started with our table of values. Okay, we're going to start with rule 1. So I'm going to come out to the left side here. Okay, I'm going to handle rule 1, which I will be putting in red. Okay, we get to make the table of values like I said. Okay, so like we normally do when we do this, okay, we are in charge of x. Okay, so we get to pick the x values, and then every x value that we pick, we will plug it into the rule, okay, to get the corresponding y value. Okay, for rule 1, the formula is 5 plus x. Okay, so we will pick our x value, plug it into the 5 plus x to get the y value, and then that will give us a point to plot. Okay, now you have to be smart about this. Okay, you cannot just pick any old x value that you want. Okay, when you look at the conditions in rule 1, okay, let me erase this. Your condition in rule 1, your x values have to be less than 0. Okay, so we need to adhere to this rule. Okay, now notice x cannot actually equal 0, but the key to getting piecewise defined functions graphed correctly is when you make your table of values, the very first x value that has to go in your table is where the rule changes. Okay, the rule changes at x equals 0. Okay, now I know this requirement here says x has to be strictly less than 0. Okay, but to get this right, okay, you have to put 0 in the table. Okay, so whenever you make a table, okay, no matter for which rule, the first thing that needs to go in your table is where the rule changes. Okay, now I need to pick additional x values. You have to adhere to this condition. I can pick anything less than 0. Okay, so I'll pick -1, -2, -3. Okay, that should be enough. Okay, so here we go. We are going to plug each one of these guys into the formula. Okay, so if x is 0, the y value is going to be 5 plus 0. That's 5. Okay, so I'm going to plot the point if x is 0, y is 5. And then I move on to x equals -1. Plug that in. We're going to get y is equal to 5 plus x, which is -1. 5 plus -1 is +4. So if x is -1, y is 4. Then plug in -2. Okay, so the y value will be 5 plus a -2, which is +3. So if x is -2, y is 3. And then I'll do one more. If x is -3, the y value is going to be 5 plus -3. That's going to be +2. So if x is -3, y is +2. Okay, so we get 4 points to plot. Okay, and you can pick more x values. The more points you plot, the better idea you get of what this looks like. Okay, we're going to go ahead and plot these points. Okay, now here's the big thing you've got to pay attention to. Okay, remember I told you the very first thing you had to throw in your table is where the rule changes. The rule changes at x equals 0. Okay, we need to go back and examine that. Okay, was it actually legal to plug in x equals 0 into this rule? Okay, well, the condition is 5 plus x is the rule as long as your x value is strictly less than 0, not actually equal to 0. So it's actually illegal to plug in x equals 0 here. Okay, so what that means for this particular point, because this is where the rule changes, this is going to be an open circle because it's not actually legal to plug in x equals 0 to this rule. Okay, this is going to be an open circle. The only possible place you can have an open circle is where the rule changes. So you can only have an open circle along this green vertical line somewhere. Okay, everything else, the -1, 4, the -2, 3, the -3, 2, those will be closed circles. Okay, again, the very, very important, the only place you can possibly have an open circle is where the rule changes. Okay, so I'm going to go to 0, 5. I'm going to put an open circle. Okay, and then -1, 4 will be closed. -2, 3 will be closed. And then -3, 2 will be closed. Okay, and you can see that the points are falling along a line. Okay, and that makes sense because 5 plus x is the same thing as x plus 5. You can put this in the format y equals mx plus b. Okay, it is nothing more than a line with slope 1 and y-intercept 5. Okay, all right, so we are going to connect the dots. Okay, but we have to be very careful about how we have to do this. Okay, remember, you don't graph the entire line. That's wrong. Okay, the graph only exists for x values less than 0. Okay, so to the left of this green dotted line. Can't cross the green dotted line. Okay, so what we're going to do here is we're going to connect the dots to the left of this green vertical line. Okay, so that's what we've got so far. Okay, cannot go this way, cannot do that. Okay, you're going to end up violating the vertical line test. Okay, however, this rule applies for x values less than 0, all x values less than 0. Okay, so remember, over here you have x values, see where my cursor is? All these x values are less than 0. So what that tells us is the graph is going to continue this way forever. Okay, and you need to put that on there. Okay, that needs to happen. Okay, so what you need to do is you need to put an arrow here to say that it keeps going this way forever. Okay, hold on, let me make sure this is pretty accurate. Remember, it has a slope of 1, so you could keep going here like this. Okay, but regardless, you don't have to add those extra points. You need to realize here that this graph is going to keep going forever. Okay, if you don't put that arrowhead there, okay, it's going to assume that your graph just stops. Okay, and that's going to change the domain of your function. Okay, so you need to be careful with that. Okay, that side keeps going forever. Okay, this is how you graph rule 1. It only exists to the left of the green vertical line. Okay, now we're going to go over to the right here and make a table of values for rule 2. Okay, rule 2 is the formula x squared. Okay, it holds if your x values are 0 or bigger. Okay, so again, x squared is one of those basic functions we learned earlier in this section. Okay, part of the library of functions. But again, to graph this out, we're going to make a table of values. Okay, we're doing this so we don't get in trouble. Okay, we get to pick the x values. we're going to plug into the formula to get our y values here. The formula is x squared, okay, which is just x times x. All right, so first thing I need to put in the table for x is where the rule changes. The rule changes because now I'm looking at this yellow rule, okay? The rule changes where x equals 0. That has to go in the table, first thing, okay? Then according to the condition, I can plug in anything bigger than 0. Okay, so maybe 1, 2, 3. Okay, that's good enough. Okay, just to get an idea of what it looks like. The more points you plot, the better it's going to look. Okay, so let's plug each of these x values in. Okay, so if x is 0, we're going to get y equals 0 squared. That's 0 times 0. That's 0. So we'll go through the origin. Okay, and then if x is 1, we're going to get y equals 1 squared. That's 1 times 1, or 1. So the graph will go through 1, 1. And then if x is 2, we're going to get y equals 2 squared. Okay, that's 2 times 2, or 4. So if x is 2, y is 4. And then if x is 3, we'll get y is 3 squared. That's 3 times 3. That's 9. So if x is 3, y is 9. Okay, so that gives us good points to plot. Okay, just like we did for the red table. Okay, before we can plot these guys, we have to check what's going on where the rule changes. The rule changes at x equals 0. Okay, so I'm concerned with this first point. Okay, was it legal to actually plug in 0 for x? Okay, and the answer is yes, because according to rule 2, your x value can actually equal 0 because of that line underneath the greater than sign. Okay, so you can actually plug this point in. Okay, so this is legal, so this is going to be a closed circle. Okay, everything else will be a closed circle. Okay, the only possible place you can have an open circle is where the rule changes. Okay, so 0, 0 will be closed. Okay, and then we've got 1, 1, we've got 2, 4, and we've got 3, 9. Okay, you can see the parabola forming. Okay, I'm going to connect the dots with a U shape. Okay, and remember, this graph holds for all x values bigger than or equal to 0. So it's going to exist for all positive x values. Okay, so we're going to keep going. Okay, so you've got to put the arrow. Okay, you cannot continue the parabola over here. Does not happen. Okay, if you put the left side of the parabola, you're going to violate the vertical line test. Okay, so that's why we've got that green dotted line there, just as a reminder. Okay, this is the entire graph. Okay, the graph is made up of the red piece together with the blue piece. Okay, the graph passes the vertical line test, including at x equals 0. Okay, because if you look at the green vertical line, okay, it would intersect the open circle, which is not included, and it would intersect the closed circle, which is fine. It intersects your graph one time. Okay, so this is the entire picture. Okay, all right, so now let's move on to the next part, because we have the graph, so we can use it. Okay, find each of the following. Okay, so we need to figure out f of -2, f of 0, and f of 3. Okay, so basically, if we look at f of -2, okay, this is saying what is the, well, let me use a different color because I don't want you to think blue is always rule 2. Okay, so let's see, what is the y value if x equals -2? That's what this means. Okay, this is a function. Every time you plug something in, you can only get one thing out. So each of these things in part B need to have one number as the answer. If you take the x value here, which is -2, and you plug it into both rules, that's wrong, wrong, wrong. Okay, this is a function. Every input needs to have a single output. Okay, so here we go. There's a couple of ways you can do this. You can either use the picture or you can use the formula. If you use the graph, here is where x equals -2. You would just go up to the picture. Okay, this point right here on the graph is -2, 3. Okay, so if x is -2, the y value is going to be 3. That's the answer. It's 3. Okay, you only, you should only have one number as your answer, not 2. Okay, the other way you can do this, okay, whatever is in parentheses is your x value. So here x is -2. Okay, you could go up to the rule. Okay, does rule 1 or rule 2 apply here? Okay, well, if your x value is -2, it falls in this category where the x value -2 is less than 0. So you would use rule 1 here. Okay, so you could plug into the rule here. You would use rule 1. Okay, so you would do 5 plus x. X is -2 here, so you would get 5 plus -2. And that's how you could also come up with the 3. Okay, so either read it off the graph or get it from the formula. But the key here is that every time you plug something in, you better have just one output. Okay, all right, let's look at f of 0. Okay, so here x is 0. Okay, so let me put this here. X is 0. Okay, so again, go to your picture. Here is where x equals 0. If you can see where my cursor is, that corresponds to the green vertical line. Okay, so you have two options here. Okay, is the output going to be represented by the red open circle or the blue closed circle? Okay, well, which one's included in the graph? Well, the closed circle. Okay, that point is the origin. Okay, so if x equals 0, y equals 0. Okay, so the answer here should be 0. Okay, again, you can look at the rule. Okay, x is 0 here, so if you go up to the rule and you figure out which one applies, well, based on the conditions, you want to go with rule 2 because of the greater than or equal to. X can actually equal 0 for this rule. Okay, so you would plug into rule 2 here. Okay, so you could do rule 2 and you would use x squared. So you would do 0 squared, you would get 0. Okay, so either use the rule or the graph. All right, lastly, if we're trying to find f of 3, that means whatever's in parentheses is our x value. So here x equals 3. We're looking for the y value when x is 3. Okay, so if you go up to the picture, okay, here's where x equals 3. If you go up to the graph, you see the point 3, 9. Okay, so if x is 3, the y value is 9. So the answer here is going to be 9. Okay, again, you could use the formula instead if you don't like using the picture. Okay, you have to figure out which rule fits the bill. If x is 9, you're going to use the second rule because 9 is bigger than or equal to 0. Okay, so you would use the second rule here. Okay, so if you come down here, we would use rule 2, which is x squared. Okay, x is 3 here, so 3 squared is 9. Okay, so that's how you want to evaluate a piecewise defined function. Remember, you cannot have two different outputs. Every input has to have a single output. All right, domain and range. Okay, this can get tricky because your graph is in pieces. Okay, let's start with domain. Okay, basically what you're going to do here, okay, I'm going to give you an easier, well, I'll show you two different ways to do this. Okay, the easiest way to do this is actually from the formula. Okay, make a number line. Okay, if you make a number line, okay, this is going to track the x values. Okay, the rule changes at 0. Okay, so rule 1 handles x values less than 0. Okay, so rule 1 does not take care of 0, but it takes care of everything less than 0. Okay, and then rule 2 comes along. It holds for x values greater than or equal to 0, so it will actually take care of 0 and then everything bigger than 0. Okay, so the entire number line is shaded. Okay, so the domain here is all real numbers. Okay, all right, that's an easy way to do it without having to confer with the graph. Okay, you could do this by the graph. Okay, you could say this red piece covers all negative x values, and then the blue piece comes along and covers x equals 0, and then all positive x values. But students often have a hard time reading the domain and range because of the pieces. Okay, so I recommend doing these little number lines to figure it out. Okay, so I'm going to go ahead and write this as the domain. Okay, we could do a similar thing for the range. Okay, I'll put it over here. We'll do one for the range. Okay, all right, so for range, we're tracking y values that this graph covers. Okay, so again, we're going to have to do this in pieces. Okay, so let's focus on the red piece. Okay, what y values does the red piece cover? Okay, well, the red piece, okay, if you look at this open circle, that point is 0, 5. So this is talking about a y value of 5. And then it covers all y values less than 5. Okay, so 5 is going to be a key point here. Okay, because this point, like I said, is 0, 5. Okay, so that is an open circle. Okay, so the red piece doesn't actually give you an output of 5. Okay, so we're having an open circle there, but it covers all y values less than 5. Okay, and then we've got to confer with the blue piece. Okay, the blue piece, okay, we're going to go from the lowest point to the highest point and look at y values. Okay, the low point here on the blue piece is the origin. Okay, so I'm going to go ahead and put a y value of 0 on here. Okay, that is a closed circle. So the blue point, the blue piece is actually going to have a y value of 0. Okay, and then after that, the high point is going to be positive infinity. Okay, so we will come in and shade to positive infinity. Okay, notice that open circle at 5 has been shaded in now. Okay, the entire number line has been shaded. Okay, so the range here is all real numbers. Okay, that might be a little confusing. Okay, it may take some practice getting used to doing these number lines to do it. Okay, but again, if you look at the picture, okay, this red piece is going down forever. So the low point is negative infinity. The blue piece is going up forever. So the high point is positive infinity. And there's overlap in between. There's no gaps. Okay, so the range, the entire y-axis is covered. Okay, this will take practice to do the domain and range of piecewise defined functions. Okay, all right, the last thing here is the function continuous on its domain. Okay, if you go back to the top, you can see the vocabulary word. Okay, a function is continuous on its domain if it has no holes, gaps, or breaks. Okay, a great way of determining continuity here, let me write something else that might help you here. Okay, oops. The way you want to think about continuity, if something is continuous, okay, that basically means if it's continuous, you can draw it without picking up your pencil. Okay, if you have to pick up your pencil to draw the graph, then it's not continuous. Okay, so when you look at this graph that we have, okay, go from left to right. Everything in this class is from left to right. So if you're on the left piece, the red piece, you're drawing blah, 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 blah. When you get to the right here to this open circle, you have to pick up your pencil to go to the blue piece. Okay, so there is a discontinuity. Okay, so the answer here, it is not continuous because you have to pick up your pencil. You may be asked where the discontinuity is. Okay, the discontinuity is at x equals 0, okay, where the rule changes, because along this green vertical line, okay, that's where x equals 0, that's where I have to pick up my pencil. Okay, I have to pick up my pencil to go from the open circle to the blue closed circle. Okay, that's happening at x equals 0. Okay, everywhere else the graph is continuous. You don't have to pick up your pencil. So you have one discontinuity, one place where you have to pick up your pencil, and that is occurring at x equals 0. Okay, so hopefully from this example, and we're going to do 3 more, you have learned how to graph a piecewise defined function. You've learned how to evaluate a piecewise defined function, meaning plug in an x value, get the output. And then we've done the domain and the range, okay, and we've talked about continuity.